it's a great pleasure to start this week's meeting of the seminar. And the lecture is Michael Lau from Laval University, who will speak about Lie algebra representations and the free Jordan algebras.
Yeah, well, I'd like to thank Ivan Kaigorodov, Uzi, and all the other organizers for the invitation. I'll talk today about some joint work with Olivier Mathieu. All of this is contained in our paper on archive, which should appear very soon in transformation groups. Uh, Feel free to ask questions at any time. Since I can't see the chat with the screen sharing, the best way is probably just to turn on your microphone and speak directly. Don't worry about interrupting me. Uh, so let's go on to the next slide. Oops, how do I advance? Hmm. Oh, I see. I have to acknowledge that it's being recorded and then it will allow me to advance? No?
Yeah.
For some reason, my slides are not advancing now. Ah, there we go. Okay. So I'll start with some reminders about past results, and then I'll discuss our category of modules of interest, the bounded modules. They're universal envelopes, and then I'll close with some finiteness theorems, which are related to free Jordan algebras. So a Jordan algebra over a field of characteristic zero is a non-associative unital algebra, which is commutative and satisfies a sort of weak associativity property, or if you like, the multiplication by x operator commutes with the multiplication by its square operator for all elements of the Jordan algebra. Uh, Jordan algebras were introduced in the 1930s in hopes of finding an algebraic home for observables in quantum mechanics. Namely, Jordan noted that while the usual product of Hermitian matrices it will not remain Hermitian in general, the symmetrized product will remain Hermitian. So he tried to axiomatize this symmetric product on Hermitian matrices, the product xy plus yx, and what axioms it satisfied. And he came up with these two axioms as the essential axioms in his mind, the commutativity and this weak associativity law. Uh, Jordan algebras have important connections to various types of geometry, as well as to the structure theory of Lie algebras, which is what we'll concentrate on today. So we'll start with some examples. Clearly, every unital commutative associative algebra is Jordan, since it's commutative and it's associative, thus weakly associative. Um, Baked into the axioms for Jordan algebras, we see that by design, associative algebras can be given a Jordan structure by using this symmetric product. Customary to put 1/2 in front so that this will generalize the ordinary product if your associative algebra happens to be commutative, or even if just A and B commute with each other, I suppose. Jordan subalgebras of this Jordan structure on associative algebras are called special Jordan algebras. So you can think about the analogy in the Lie algebra setting here. So in Lie algebra setting, given any associative algebra, you can build a Lie algebra out of it just by taking the antisymmetric product AB minus BA. However, this notion of a special Jordan algebra doesn't really have a very interesting analog in the case of Lie algebras, because of course, by the Poincare-Birkhoff-Witt theorem, every Lie algebra embeds in its enveloping algebra. So every Lie algebra is special in this sense. But for Jordan algebras, uh, it turns out that almost every Jordan algebra is special, but in a striking result in 1979, Zelmanov showed that the only simple Jordan algebras which are not special are 27-dimensional Albert algebras over their centers. In the case of working over an algebraically closed field, uh, Albert algebras can be realized as Hermitian 3 by 3 matrices over the split octonions. Another interesting source for Jordan algebras is the case of free Jordan algebras. This is much more delicate than free algebras in other settings. For example, it may be surprising to know that free Jordan algebras in sufficiently many generators, I think even just three will work, actually contain zero divisors, which is a little bizarre for a free object. So in the case of a free Jordan algebra in one generator, well, t associates with t squared all the time, and etc. So, in fact, the free Jordan algebra in one generator is just the polynomial ring, the ordinary associative commutative polynomial ring in one variable. Free Jordan algebra in two variables is in fact special. It embeds in the free associative algebra on two generators as the set of so-called reversible elements. So these are palindromic elements, so that if you read them going forward or you read them going backwards, you get the same thing. However, as soon as you move to three generators, the free Jordan algebra on three generators is no longer special. Uh, there's a there's a rather complicated degree 8 identity due to Glenny in the 1960s in three variables, which is not the zero element of J3, but it vanishes on all special Jordan algebras. So this is called Glenny's identity, and it proves that J3 is not special. Today we'll be interested primarily in the connection between Jordan algebras and Lie algebras. Um, Tits showed that given a Lie algebra with grading by the root system A1 of an SL2 subalgebra, its top eigenspace can be given a Jordan algebra structure. So how does this work? Um, so if you want to multiply two elements x and y, which are in the top eigenspace, G2. So this is all eigenspaces with respect to the Cartan element of the SL2 subalgebra, which is living inside of G. So first you take the Lie bracket with f. So that's going to drop you down to the G0 component. And then you take the Lie bracket again with y, which moves you back to the G2 component. So at least you can see that x dot y is going to be some bilinear map, which is going to move you from G2 cross G2 into G2, which is a good thing. And in fact, this gives you a Jordan algebra structure. You can also go the opposite way. So this was also done by Tits, or a version of this was done by Tits, and later generalized by Kantor and Koecher to first Jordan triple systems and then to Jordan pairs. We're going to use a universal version of this due to Allison and Gao in the late 1990s, which has the advantage that unlike the original Tits-Kantor-Koecher construction, the universal version is functorial. So what you can think of this as is you're trying to build a Lie algebra structure out of SL2 with entries in your Jordan algebra J. The problem is that when you look at the Jacobi identity, the non-associativity of the Jordan algebra is going to screw things up. So you need to correct for this by adding some sort of thing that will function as derivations in order to fix the non-associativity problem to remedy the Jacobi relation. And this J curly bracket J here is an abbreviation for looking at the wedge product of J with itself modulo this structure here. So this is based on generalizing a cyclic homology construction of the universal central extension in the case where J happens to be associative and commutative. So the point is this structure here can be made into a Lie algebra with a certain Lie bracket. So there's not much that I really want you to retain out of this out of these formulas, which probably at first glance look rather complicated, but actually are quite nice when you start to work with them. But I guess I would like you to note a couple things. So one, if you look at the first relation here, can you see this dot that I'm using the pointer on the screen? Okay, good. Very good. Then I'll continue to use that as needed. This first relation here, think about what happens if you take the Cartan element H of your Lie algebra SL2, tensor A, with another H tensor B here, your first term here is going to be 0, and your second term is just some scalar times A comma B. So what this is saying is that the elements H tensor A are actually generating everything in the things like H tensor A and together with these JJ terms. You can get them all out of that. So that's something we'll come back to later on. The other thing I want you to note from this is from the third relation down here, the A curly bracket B bracketed with C curly bracket D, you see that the curly brackets are closed under the Lie bracket, which is to say that this J curly bracket J object is actually a Lie subalgebra of the resulting Lie algebra here. So now we have a way to go from SL2 graded Lie algebras down to Jordan algebras just by looking at the top graded component there, the G2 component relative to the add H action. And we've got a way to go back, namely to start with the Jordan algebra and move backwards to a Lie algebra. And in fact, these are adjoint functors. Bruce Allison, Yun-Gao, and Erhard Neher in 96 showed that, in fact, every A1 graded Lie algebra is a central quotient of some SL2 hat J for some J. So A1 graded here means that we have an SL2 subalgebra of our Lie algebra, and the Lie algebra is generated by the non-zero root spaces. Okay, some examples. So for first example, of course, every commutative associative algebra is a Jordan algebra. So we could consider the Laurent polynomials in one variable. That J curly bracket J is in fact one-dimensional in this case. As I mentioned, this is a generalization of cyclic homology, or also Kähler-1 forms, modulo exact forms. And this is this gives you exactly the affine Kac-Moody algebra, A11. In greater generality, if you just take R to be any unital commutative associative algebra, you are in fact getting the universal central extension of this SL2 over the unital associative commutative algebra R. Of course, we want to know what happens when we apply this construction to perhaps the most interesting, or at least the most exotic, of our Jordan algebras, which is the Albert algebra. So if we apply the construction to the Albert algebra, I'm going to write on here. We can count some dimensions here. So we have a three-dimensional SL2, and then we have this 27-dimensional Albert algebra. It's not readily visible what the dimension of A curly bracket A is, so I'll just tell you it's 52. And if we add up these dimensions here, we get, let's see, 81 plus 133, plus 52 makes 133, which is a rather suggestive number for Lie theorists, because you may remember that this is the dimension of E7. And in fact, this is exactly a construction of E7 here. Meanwhile, living inside this SL2 hat A, we have the Cartan subalgebra, one-dimensional of SL2, and our 27-dimensional Albert and our 52-dimensional A curly bracket A, which is very close to a suggestive number in Lie theory. 79 is almost the dimension of our exceptional Lie algebra E6, which is 78-dimensional. And in fact, this is a direct sum of E6 and a one-dimensional trivial Lie algebra. And of course, 52 is also a special number. And so this is F4. So you can see that this Tits-Kantor-Koecher construction, or which is the same as the universal one in this case, is quite useful for constructing exceptional Lie algebras. In fact, even E8 can be constructed by some sort of extended version of this construction, which you can find in an old and quite forgotten, unfortunately, book of Jacobson on exceptional Lie algebras and on constructions of them. And G2 is linked into all this too as the derivations of the octonions, which are living inside A, since it's uh, the Hermish 3 by 3 Hermitian matrices over them. Okay. Okay. So today I'd like to look primarily at a category of what are called bounded weight modules. So first of all, what do I mean by weight module? The weight modules here are going to be weight modules with respect to the action of the SL2 carton living inside. So we just have the single carton element H tensor 1, which we'll abbreviate as H1, and we decompose, we want to be able to decompose our module into eigenspaces with respect to this single operator here. We call it bounded if it has only finitely many non-zero weight spaces, but we are allowing the weight spaces to be potentially infinite dimensional here. Some observations. If you have a bounded weight module for G, which will be our notation for SL2 hat J, then by SL2 theory, clearly the weights all have to be integers. The G2 invariance, so remember G2 is the two weight space relative to the add H action on G, is a module for the G0 space. And the W that we start with is in fact a quotient of a Verma module. So we can first build a Verma out of the G2 invariance by letting the G2 piece act as 0, of course, and then the G0 piece acts on V, and we induce upwards to get a module for all of G. And finally, there's a copy of J, namely H tensor with J, which remember generates G0. So G0 here is just this H tensor J plus JJ. And remember the things like H tensor little h tensor little a generate things like J comma J just by our relations in the universal Tits-Kantor-Koecher construction. So J generates all of G0, which means that we could really look at this top space V purely in terms of an action of the Jordan algebra on it, instead of looking at the action of a Lie action on it. But not every action of the Jordan algebra on there is going to give us a G0 module. So we have to ask what sort of actions are allowed of our Jordan algebra J on this vector space V that will give us a G0 module. So this is just coming down to looking at what those defining relations are, the commutation relations for our Lie algebra G0. And we get these two relations here when we just compute explicitly. These are in fact also the relations to have a representation of a Lie triple system. Lie triple systems were designed after this Tits-Kantor-Koecher construction, so that's not too surprising. Just to have the terminology, a homomorphism of J spaces is going to be exactly what you'd expect. It's a linear map between these J spaces that commutes with the action of J. Okay, so now you'd like to know probably why we call this J space and not J module or J bimodule. So, of course, in non-associative algebra theory, we typically have a theory of bimodules for the non-associative algebra, and the theory goes that a vector space is going to be a bimodule in the appropriate category of non-associative algebras if the semi-direct product of the non-associative algebra with this vector space with the appropriate actions gives you an algebra in the right category. So if J is commutative and associative, being a J module in the usual sense will imply that you're a J space, but the reverse implication is not true. So an example that we've already more or less seen was if you take J to be the Laurent polynomials in one variable, then remember that this Tits-Kantor-Koecher construction gave us the affine Lie algebra, SL2 hat. So the G0 piece of that will be the infinite dimensional Heisenberg. And we know that the infinite dimensional Heisenberg algebra certainly has many, well, many in some sense, just one in another sense. It has interesting representations in which the central element acts non-zerally, which means that these representations are going to be J spaces, because remember, a J space is the same thing as a G0 module. But on the other hand, they're not going to be J modules, because a J module here has to be a module in which X and X inverse commute with one another, which they certainly don't in the Heisenberg. More generally, if J is a Jordan algebra, Jordan bimodules are J spaces, but J spaces need not be Jordan bimodules. This is a more general notion. Um, this is coming because for Jordan bimodules, the constants by which an idempotent can act are severely limited by the Peirce decomposition. And for J spaces here, our idempotent 1 is much more free to act by different values. Okay, so since our primary construction so far for constructing bounded modules is to look at quotients of generalized Verma modules, we can ask the question about which J spaces lead via the Verma construction to a bounded quotient. Not every J space will have a bounded quotient. So we define a J space to be dominant if the resulting Verma module has a bounded quotient. So bounded, again, remember, means that it will have only finitely many weight spaces relative to this action of H tensor 1. And our space V embeds into the G2 invariance. So the thing to keep in mind is sort of like you have the V at the top. So for example, the simplest example would be to take our Jordan algebra, just the commutative associative algebra C. So now what happens? Tits-Kantor-Koecher algebra is SL2C. G0 is the one-dimensional Cartan. Now the question of being dominant, so which modules for this one-dimensional Lie algebra CH are going to induce to modules with some quotient which is bounded. It just means that, well, the action of H tensor 1, which is this row of 1, because remember, row of A is the action of H tensor A for any A. So row of 1 has to be, namely the action of H. H has to be diagonalizable with finitely many eigenvalues. And they've got to be dominant integral highest weights for our modules. So these have to be non-negative integers here. Otherwise, we're going to have a Verma which is within there, which is irreducible, and we won't be able to cut the weight spaces down to a finite number in a quotient. In fact, we can simplify our discussion a little bit because H tensor 1 is central in the Lie subalgebra G0. It commutes with everything like H tensor A, and it commutes with our A curly bracket B. So this means that the H1 eigenspaces are themselves G0 submodules. So without loss of generality, we can just split up the J space into H1 eigenspaces and just consider the case where H1 is acting by a constant on the entire J space. And so we're going to call this constant the level. So here are some examples. If V is a dominant J space of level 0, this is the same as saying that the action of our Jordan algebra J has to be trivial. J has to act as 0 everywhere. Dominant of level 1 is the same as saying we have a Jordan homomorphism from our Jordan algebra J into the plus algebra. Remember, you take an associative algebra but equipped with this symmetric product. And this is a Jordan homomorphism from J into NV plus. So this implies in particular that V is going to be a Jordan bimodule. Being dominant of level 2 is the same as saying you have what's called a multiplication specialization of the Jordan algebra, which again implies that V is a Jordan bimodule. So the idea of a multiplication specialization is that the Jordan algebra J is acting like multiplication left multiplication operators on some perhaps larger Jordan algebra that contains J. Finally, being dominant of level greater than 2 by these Peirce decomposition restrictions, V is never a Jordan bimodule. However, there exist such examples. So, for example, in this free Jordan algebra of rank 1, the map that rho, which is taking KT, the polynomial algebra, into the symmetric endomorphisms of the symmetric polynomials, taking each t to the L to multiplication by the Lth Newton polynomial, in fact, gives you a gives you a dominant level n J space structure on the symmetric polynomials in n variables. So there are many examples. Okay, we'll look at Weyl modules. So Weyl modules are the maximal bounded quotients associated with a J space. So they're defined for any J space, even if our J space isn't dominant. But this Weyl module here could become zero in that case, or could be something in between. It won't contain all of V in that case. So what we're doing here is we're taking the Verma module, and then we're modding out. We're modding out by everything that we need to mod out by in order to make this quotient be bounded, but just the minimal amount of bounding out. So this is the maximal bounded quotient of the Verma module associated to a J space V. But keeping in mind that this could be zero, the top space this could be zero, or the top space could be something smaller than V. So some properties of these Weyl modules: if both your Jordan algebra J and your J space V are finite dimensional, then of course, because you have only finitely many weight spaces in the Weyl module, and you only have finitely many ways to go down from a finite dimensional space by applying things like F tensor A, your Weyl module is forced to be finite dimensional as well. In the case that J is finite dimensional and simple, your resulting universal Tits-Kantor-Koecher algebra is also going to be finite dimensional and simple. And in fact, there's a bijection between the simple dominant J spaces and the finite dimensional simple G modules, just sending each simple dominant J space to the resulting Weyl module, delta V. And to go in the reverse direction, you look at the G2 invariance. So again, remember G2 is the space, well, I can say explicitly what it is. It's the space E tensor J living within this Tits-Kantor-Koecher algebra G. So in fact, to extend this observation, this bijection here, in fact, we have again a system of adjoint functors here. So if we look at the category of bounded G modules with highest weight n and dominant J spaces of level n, then this delta functor is actually adjoint to the take the top space, take the n space of your module functor. Another example is look at this G2 space. So this is this E tensor J here. So this is a J space of level 2. We certainly know that it's going to be a dominant J space of level 2 because this is part of G after all, and G is an adjoint G module, and that's certainly a bounded weight module for G. So this is a J space of level 2. By the universal property listed above, the number 3 up there, there's going to be a unique G equivariant homomorphism from the Weyl module down to G here. which allows you to put a Leibniz algebra structure, a left Leibniz algebra structure on delta J here. Namely, if you want to take the Leibniz bracket of two elements in delta J, what do you do? Well, you project the first one downward into G, and then you let it act on the second one because delta J is, after all, a G module. So in fact, this is a way to construct the the universal central extension of G in the category of Leibniz algebras. We can reformulate our dominance question. Remember, the question of being dominant was when you ask, does a V embed into a bounded quotient of the Verma module associated with V. So we can reformulate this a little more concretely by asking which J spaces embed in the Weyl module, knowing that that's the maximal bounded quotient that we can possibly have of V. So here's a criterion determining when a J space is dominant. So a J space of level n is dominant if and only if this combinatorial condition holds. So the sum taken over all partitions of n plus 1 of the sign of the permutation being any permutation with this particular cycle structure, times the cardinality of the conjugacy class of permutations with this cycle type, times this operator rho sigma A defined below is equal to 0 for every element of the Jordan algebra. So you might wonder where this comes from. So I'd like to take a moment to explain the main ideas of the proof. So V being dominant is, what does this say? Well, this says that V is embedding in this Weyl module. So that's to say that if we take the bad spaces of the Verma module, so those which have weights that are outside of the desired collection of weights. So we know that the top space is going to be weight n. So if we have a bounded quotient, we're going to need the bottom space to be of weight minus n. So if we fall below minus n, that has to be eliminated in the quotient. So we look at the module generated by these bad spaces here, and this module has to be disjoint from the top space because we need V to embed in there, and the top space initially is V itself. And if this submodule generated by the bad spaces intersects the top space non-trivially, then it's going to eliminate something at the top, and we won't have V embedding in there. So in other words, this is the same as saying, if we go down in all the different ways possible from something on the top, far enough that we fall into a bad space, and then we move upwards, when we get back to the top, we have to have 0 there. So you can say, well, why do we have just 1 here in A when you said in all the different ways possible? This is the magic of linearization here that you can simplify to this case here. So this is the relation then that we need. To be dominant is exactly that this relation here holds for every A in the Jordan algebra J, and for every V in the top space here. How do you calculate if this is equal to 0 or not? Well, what you need to do is you need to turn around these E's and these F's using the PBW theorem. So what we're really doing is we're taking a Harish-Chandra projection from the universal enveloping algebra of our Tits-Kantor-Koecher algebra to this piece right here. So the piece given by the 0 and the minus 2. So if there's any 2 piece there, any G2, that's going to kill our vector V, because our vector V is something that's living in this J space, and in the Verma module construction, it's going to be killed by all the positive piece of our Lie algebra. So we take this Harish-Chandra projection here. How to calculate the Harish-Chandra projection explicitly? We use exponential generating functions to describe how to re-express. Хорошо? Bon. Okay, so this yeah, so we turn these around. We write this out in terms of an exponential generating function, and then we can calculate the coefficients of the powers in this exponential generating function using symmetric group combinatorics. In particular, this expression here is coming out of the Newton-Girard identity. A version of Newton-Girard looks a lot like this expression here. The beauty of this is that this lets us define universal envelopes for dominant J spaces. So the dominance theorem uh, gives us um, uh, a universal envelope for each dominant J space. Namely, we want to look at the modules. So a J space is just a module for G0. So we want to look at the modules for G0, i.e. the modules for the universal enveloping algebra of G0, modulo the conditions that define that our J space should be dominant. So what are the conditions? So to be dominant of level n means that H tensor 1 has to act as n. And then this is exactly our dominance condition here, is that this expression here has to be 0. So we quotient out by the space spanned by the ideal generated by these relations here. So by construction, the UNJ modules are the same thing as dominant J spaces of level n. So let's see some examples. From our previous observations, we see that to be a U1J module, the U1J is going to be exactly the universal unital special envelope of J. U2J will be the universal unital multiplication envelope of J. And UNJ, for larger n's, are going to give us more invariance for Jordan algebras, which perhaps have not been previously looked at. So some examples. If J is the free Jordan algebra on one generator, then UNJ is just going to be the algebra of symmetric polynomials in n variables. The isomorphism, explicit isomorphism, associates T to the L to the Else-Newton polynomial. If J is finite dimensional, then UNJ is also going to be finite dimensional. If J is finite dimensional and simple, UNJ will be semi-simple. What happens in the case of the Albert algebra? If you start with a split Albert algebra, then SL2 hat A, as we saw, is going to be E7. With a careful choice of the root basis, we can express the element H of the copy of SL2 living inside E7 in terms of the co-roots as follows, in this expression here. If it happened that our universal associative envelope were non-zero, then this would mean that we would have some finite dimensional simple E7 module for which this element H here acts as 1 on the highest weight space, because the highest weight space is going to live inside this G2 invariant space. But this is impossible because if you look at the coefficients that appear in the expression in terms of co-weights here, if you apply any dominant integral highest weight to that, there's no ones as in coefficients here, so it's impossible to get lambda of h is equal to 1. So as a consequence, we see that u1 of a has to be 0. And that's another way of just saying that A is an exceptional Jordan algebra. So we believe this to be a new proof that the Albert algebra A is not special. Using the TKK construction. These universal unital envelopes might also dominant envelopes might also be interesting as a form of invariance for affine varieties. They seem to capture some of the geometry of affine varieties. In general, these are going to be non-commutative algebras here, and in fact, we can show that they're non-commutative for all varieties which have a tangent space of dimension at least 2. So, for example, a singular curve. This would be non-commutative algebra. Okay. Uh, in the last few minutes, I'd like to talk a bit about some finiteness theorems, which should be thought of as being applied to free Jordan algebras. Um, the, uh, these theorems are in fact uh, the proofs are rather delicate, and they're deeply connected with Zelmanov's fundamental result that finitely generated nil Jordan algebras of bounded index are nilpotent. Yeah, so let's go through some of these. So if J is a finitely generated Jordan algebra, so each time just think in your head about these Jordan algebras as being free Jordan algebras. So if you have a free Jordan algebra on finitely many generators, then these universal envelopes are all going to be finitely generated associative algebras. So this generalizes some known results for the cases where n is equal to 1 and 2, namely that if J is finitely generated, it's known that the universal unital special envelope is finitely generated, and that the universal unital multiplication envelope is finitely generated. Okay, next, let's look at Weyl modules. If J is a finitely generated Jordan algebra with codimension 1 ideal, so again, think about the case of a free Jordan algebra. So the codimension 1 ideal here is just the augmentation ideal generated by the generators. Remember that our Jordan algebras are unital. So you have this codimension 1 ideal, and let V be a smooth dominant J space. So smooth means that for every element of your J space, H tensor sufficiently high power of this augmentation ideal applied to V is equal to 0. The power depending on allowed to vary according to the element little v. Then the Weyl module will be finite dimensional if and only if the J space is finite dimensional. So we already saw this in the case that J was not just finitely generated but finite dimensional. And in that case, this was easy. Here, this requires Zelmanov's theorem on the nil and nilpotent Jordan algebras. So in particular, this says that the category of finite dimensional smooth SL2 hat J modules contains its Weyl modules and their duals. This is suggestive of a highest weight category, and in fact, it has a lot of commonalities with highest weight categories. It's locally Artinian. It has simples, standards, or co-standard objects of finite length and their injective hulls labeled by a poset. But it lacks enough X vanishing to be a highest weight category. So, for example, there are non-trivial self-extensions in this category, unlike in highest weight categories. Finally, we'll look at the Tits-Kantor-Koecher algebras themselves. If J is finitely presented, then the associated Tits-Kantor-Koecher algebra is also finitely presented. Or related, more general question, we can talk about Lie algebras of type FPN. So a Lie algebra is of type FPN if the trivial module for the Lie algebra has a projective resolution with each of the terms up to the nth term being finitely generated. If the Lie algebra is FPN for every n, then we call the Lie algebra FP infinity. So in particular, finitely generated implies FP1, finitely presented implies FP2. So we might wonder, how far can we push this? In the case of the free Jordan algebra of rank 1, this is FP infinity. We might wonder, is it also true that for the free Jordan algebra of rank R, is that also FP infinity? Our theorem is that if SL2 hat JR plus 1 were FP infinity, we can show that there's enough cohomological vanishing to prove a conjectural formula for the graded dimensions of the free Jordan algebra on our generators. However, Dotsenko and Hensel have posted on arXiv a very interesting preprint in which they gave a counterexample to this conjectural formula with computer calculations. I've looked at the relevant section and the calculation. While I haven't checked the calculation, of course, it seems to be relatively straightforward the process because you're working inside J2 here, and remember J2 is this special Jordan algebra which you can compute explicitly on because these are the reversible elements inside the free associative algebra on two generators here. So the degree 19 elements. So degree here is the total degree as a polynomial in your two variables here. But because we're in this non-associative algebra, you're allowed all kinds of different arrangements of your parentheses here. So this is dimension 262,656 rather than the predicted value of 262,658. So the corollary is that this formula that's conjectured by Kashuba and Mathieu is in fact false, which for our theorem then shows that we have a negative answer to our question about FP infinity. In fact, SL2 hat JR is never FP infinity when R is at least 3. So the 3 versus 2 is because of this décalage in the R plus 1 here and R over here. So, oops. Okay, there we go. Yeah, so as I mentioned, the proofs of these three finiteness theorems are non-trivial, and they're tied to this result of Zelmanov. So that's all I had planned for my talk. So, thank you.
Thank you very much. Are there any questions? So before someone else gets in, I have a question.
Yeah.
This difference of 2, precisely 2 in the identities, it reminds me of the Glenny identities, where there are 2 identities in degree 8, and they
Yeah.
measure the failure to be special, in a sense. Can you say
Okay.
something of this type? What is the failure of, what property fails for this difference to exist? What does it measure?
I don't know. That's a really interesting idea though to tie it to Glenny. Honestly, in their paper, they basically just say that in Dotsenko and Hensel's paper, they basically just say that well, we calculated these things in the straightforward way, and we see that the numbers aren't the same, so the conjecture is false. But
Has to measure
yeah,
something.
I don't know what's special about degree 19 also. They calculated everything before it too. I don't know that they had any intuitive reason to believe that 19 was the magic number. They just calculated further than anyone else had calculated before until something failed.
So we are lucky they didn't get tired in 17 or 18. Okay. Any other questions? Well, so thank you for a very interesting talk, very enlightening. So thank you again, and we'll meet next week.
Yeah, thank you for the invitation. Okay, goodbye.
Bye bye, Mike.